If you've ever imagined a future where humans travel beyond Earth and build permanent outposts across the solar system, that future is no longer just an idea. Humanity has already taken its first real step back into deep space. The Artemis program is not a promise of what might happen. It is the beginning of what is already happening. Named after the sister of Apollo, the Greek goddess of the moon, Artemis represents a continuation of one of humanity's greatest achievements. More than 50 years after the first moon landing, humans have once again returned to the space around the moon. But this time, the goal is not just to visit, it is to build something that lasts. The vision goes far beyond a single mission. It includes building a permanent presence on the moon and using it as a foundation for the first human journey to Mars. To reach that point, NASA had to prove that its new systems could survive the harsh reality of deep space. From extreme distances to constant exposure to solar radiation, years of delays, redesigns, and testing were not setbacks. They were the cost of building something that has never existed before. That moment has now passed. Artemis I successfully demonstrated the system. Artemis II has already carried astronauts back into deep space, farther than any human has traveled in more than half a century. The question is no longer whether this can be done. The question now is what comes next. Because what you are about to see is not just a mission, and not just a return to the moon. It is the early stage of a system designed to take humanity beyond it. Artemis I launched from Launch Complex 39B at the Kennedy Space Center and marked a turning point in modern spaceflight. For the first time, said NASA's Space Launch System, a super heavy rocket, carried the Orion spacecraft beyond Earth, proving that a new generation of deep space systems was no longer theoretical, but operational. Although Artemis I carried no human crew, Orion was built for them. The spacecraft is capable of supporting up to 6 astronauts, equipped with solar arrays for power, a fully digital glass cockpit, automated docking capability, advanced life support systems, and a launch abort system designed to pull the crew to safety in the event of a catastrophic failure. Its propulsion system combines a main engine with multiple maneuvering thrusters, allowing precise control throughout the mission. Artemis I traveled far beyond the moon and returned safely to Earth, spending several days in a distant retrograde orbit, a path that allowed engineers to test how the spacecraft behaves in deep space over extended periods of time. Alongside the main mission, a set of small secondary payloads were deployed, including compact satellites designed to study lunar resources and test new propulsion concepts. These experiments extended the mission beyond a single spacecraft, turning it into a broader testbed for future exploration technologies. At the center of it all was the Space Launch System, standing over 100 meters tall and generating nearly 9 million pounds of thrust at liftoff. It is the most powerful rocket ever built, designed not just to reach orbit, but to push heavy spacecraft out of Earth's gravity and into deep space. During launch, like the core stage and 2 solid rocket boosters ignited together, releasing an immense amount of energy within minutes. The core stage consumed millions of liters of propellant, while each booster burned through vast quantities of solid fuel, a level of power that is difficult to fully grasp without witnessing it firsthand. But Artemis I was not just a demonstration, it was a validation. And with Artemis II, that same system has already carried humans back into deep space, transforming what was once a test into a proven capability. What follows after launch is not just raw power, but precision. As the engines ignited and the vehicle climbed, the core stage and solid boosters eventually exhausted their fuel and separated, allowing the rocket to shed weight and continue its ascent. At that point, the Space Launch System had already reached low Earth orbit. But escaping Earth's gravity required something more. That moment comes with a maneuver known as trans-lunar injection. The upper stage ignites again, accelerating Orion to the speeds approaching 25,000 miles per hour, fast enough to break free from Earth and begin its journey toward the Moon. Once that burn is complete, the stage separates, releasing a set of small satellites, each carrying out its own independent mission, while Orion continues alone into deep space. As Orion approached the Moon, its maneuvering engines adjusted its trajectory, guiding it behind the far side, a region where communication with Earth is completely lost. From there, the spacecraft used the Moon's gravity to curve its path and begin the long journey back home before re-entry. Orion separated from its service module and plunged into Earth's atmosphere, protected by its heat shield, before deploying parachutes and splashing down in the ocean. This sequence may sound familiar, but the scale is entirely different. The Space Launch System is designed to carry heavier payloads and send humans farther than any previous system. This capability is not just about reaching the Moon, but about building the capacity to support complex missions that extend far beyond it. Artemis I carried no human crew, but it did not fly empty. Inside Orion were instrumented test bodies, including a mannequin equipped with sensors to measure radiation and acceleration, along with additional test units designed to simulate human tissue. These were not symbolic passengers. They were collecting data that would define the safety limits for future astronauts. Some elements were therefore tradition, small objects carried along for the journey. But the core of the mission focused on understanding one thing: how the human body can survive beyond Earth's protective magnetic field. Sensors embedded within these test systems recorded how radiation interacts with different types of tissue, providing insight into risks that cannot be fully reproduced on Earth. That data did not stay theoretical. It directly informed the systems used in Artemis II, where astronauts experienced deep space conditions in reality, not simulation. What was once measured through instruments has now been felt by humans themselves. Humans have walked on the Moon before, but only a small number of them, and all of them men. Artemis is changing that. It is designed to send a more diverse group of astronauts beyond Earth's protective magnetic field into an environment where radiation is no longer filtered, and every moment in deep space carries measurable risk. What was once theoretical is now something astronauts have begun to experience again. The data collected during Artemis I was not the end of the process, but the beginning. It helped define how spacecraft systems and human bodies respond to deep space conditions. And with Artemis II, that knowledge moved beyond simulation. As astronauts traveled around the Moon and returned, confirming that these missions are no longer experimental, but operational. With that milestone achieved, the roadmap has evolved. The next phase is no longer about simply reaching the moon again, but about building the systems required to stay there. Instead of rushing directly into a landing, NASA is focusing on testing the infrastructure in stages, ensuring that every component works as part of a larger system. The upcoming missions reflect that shift. The next mission will focus on operations closer to Earth, testing how spacecraft rendezvous, dock, and integrate with other systems. Only after those capabilities are fully proven will the program move forward to a sustained human presence on the lunar surface, beginning later in this decade. Supporting all of this is the development of the Lunar Gateway, a space station that will orbit the moon and act as a hub for future missions. Unlike past stations, this one is being built specifically for deep space operations, with power systems, docking ports, and living modules designed to support long-duration missions far from Earth. On the surface, plans are already in motion for a long-term base near the lunar South Pole, where water ice and other resources can be used to support human life and future missions. Vehicles designed to traverse the surface, along with pressurized rovers that allow astronauts to live and work without constant exposure, are all part of a system that is being engineered piece by piece by. This may sound like exploration, but it is something more structured than that. The goal is not simply to visit the moon again, but to learn how to operate there continuously. Before the moon can become accessible, it must first become livable. Which leads to the real reason behind all of this. The return to the moon is not happening in isolation. It is part of a larger shift. Competition between nations is accelerating, and space is becoming a domain where technological capability defines influence. The moon offers resources, positioning, and a testing ground that cannot be replicated anywhere else. But beyond competition, the deeper purpose is preparation. Every system tested on the moon, from life support to propulsion to surface operations, is part of a larger objective. The moon is not the destination, it is the proving ground for what comes next. The next phase of this journey is already being prepared. More powerful versions of the Space Launch System are being developed, designed to carry heavier payloads and support missions that extend far beyond the moon. Each upgrade is not just an improvement in performance, but a step toward a capability that has never been achieved before. The long-term objective is clear: to move beyond lunar missions and begin the first human journeys toward Mars, not as a distant dream, but as a sequence of problems being solved one step at a time. Every system tested, every mission completed, is part of that larger trajectory. And what once depended on a single mission no longer does. Artemis I proved the system. Artemis II proved that humans can return to deep space and come back safely. What happens next will determine how far that capability can be extended. More than half a century after Apollo, humanity has crossed that distance again. But this time we are not just visiting, we are learning how to stay, how to operate, and how to build beyond Earth. Because the return to the moon is not the final step. It is the beginning of a system that reaches far beyond it. And if this is the kind of journey you want to follow, not just the missions, but the deeper story behind them, then stay with us, because this is only the beginning. Subscribe, and you'll see not just where we are going, but why it matters and what it means for the future of humanity beyond Earth.